This video is going to show you how to solve the solution to projectile motion problem number 8 from our workbook. An arrow shot up at a 37-degree angle with a horizontal. The arrow leaves the bow traveling 68 meters per second. Eventually it lands on the ground. The arrow is going to land at the same height it takes off from. So this is what I was calling a symmetrical projectile motion problem. In other words, the initial velocity equals the final velocity, the initial angle equals the final angle, and the total displacement between the beginning and the end, the vertical displacement, is equal to 0 because there's no change in elevation between where it starts and where it stops. To start solving the problem, we'll begin with the initial velocity and make it into a right triangle. I'll start by drawing 37 degrees and 68 meters per second as the initial velocity. Make that the hypotenuse of a right triangle, and notice how my arrows connect tip to tail. The side adjacent to the angle 37 degrees uses the cosine function, so that becomes 68 meters per second cosine 37. The side opposite 37 degrees becomes 68 meters per second sine function, because sine is associated with the opposite side. So now I've broken apart my initial velocity into vertical and horizontal components. I can put them in my table. So my data table, I'm using VOXTVA, V-O-X-T-V-A. And then vertically, I know it's going up 68 meters per second sine 37, so that's a positive value because it's going up. The total displacement vertical, the difference between where it starts and stops, is 0. And when the acceleration is equal to negative 9.8 meters per second squared going downwards. Horizontally, I know the velocity is 68 meters per second, and horizontally there are no forces acting on it left and right, so that makes the acceleration horizontally equal to 0. Now I can start looking at the questions. The first one's an apogee question, because it's asking how high above the ground did the arrow travel, neglecting the height of the bow from the ground when shot, so basically everything shot at ground level. Well, when looking at this problem, I've changed my data table a little bit just for this problem, because apogee is defined as where the vertical velocity is equal to 0. So for the sake of part A, I'm changing my data table. I don't know what x is, that's what I got to find, and now my final vertical velocity is equal to 0, because that's a definition of apogee. So I'll use kinematics and the givens in the vertical column in order to find the height to apogee. So I use the v-squared formula, and I get the height to apogee to be 85.45 meters. Next question, how long was it in the air? So I'm looking for the total time it's in the air. Notice my table of givens has changed back to the original form. My vertical x is equal to 0 because the total time in the air, the difference in the vertical heights, is equal to 0 for the total time it's in the air. So to find out how long it's in the air, I'm looking at my givens. I need at least 3 givens to figure out that answer. I don't have 3 in the horizontal column, but I do have 3 in the vertical column. So I'm going to use my vertical givens and time. So I need an equation with v0, x, t, and a in order to find the time it's in the air. So that's the long equation. And when I solve that, because it's a quadratic equation, I use a quadratic formula and I get 2 answers. One of them is t equals 0, and the other one is t equals 8.35. And they're both true because at a height of 0, that's at the very beginning of the motion and the very end of the motion. So at 0 at the beginning and the end at 8.35 seconds. So 8.35 seconds becomes my time. Next question, how far across the ground did it travel? So this is a range question. I'm looking for a horizontal distance. So if I look at my horizontal givens up there at the top, I can see that I have the velocity and the time. Acceleration is equal to 0, and all I need is the x. So to do that, I'm going to use my range equation and just the horizontal givens. Remember, looking back, that time is in both columns because time is a scalar, so you can put it in both columns, and that's where my time came from in the horizontal column. Putting my numbers in, I get the range is 453.56 meters in the same direction as the velocity.